Welcome. Thank you for joining, everyone. Today is the first webinar in the new RAVENNA Fall webinar series, and it's mostly about remote sessions. So let's begin. First of all, my name is Andreas Hildebrand. For those who don't know me, I'm working as a RAVENNA evangelist at ALC Networks here out of Munich. The company has been established back in 2008, and its sole purpose, the sole task, is to develop and maintain the RAVENNA IP media networking technology, which I guess I don't have to introduce in detail anymore. Our guest today will be Nicolas Sturmel from Merging Technologies. Nicolas is the media network and interoperability expert at Merging and also the Animan product owner. He has a background in computer technology. He's very passionate about audio networks, and he's also a member of the AES Standards Committee, which is maintaining the AES67 standard. And he is actually leading a current activity of that group, which is, how can it be otherwise, the AES67 over WAN activity group. One word about Merging Technologies as they celebrate their 30th anniversary this year. They are the designer of Horus, Happy, and other very, very fine analog to AES67 converters using RAVENNA technology. And they are, of course, also very famous for having developed the Pyramix digital audio workstation. So the remote sessions, they comprise of a series of 6 webinars with focus on remote production. And we will cover fundamental basics and educate on theoretical principles, but we will also provide some practical experience, and we will also have the one or the other, hopefully very valuable tip and trick in the bag for you. The whole series is not completely focused on remote production. We have one webinar which is coming next week, which focuses on 2110-31 applications. That's the area where next generation audio plays a very important role. And one of those remote session webinars will focus on timing and synchronization again, including introduction on the enhancements of the released PTP version 2.1 standard. All the webinars are taking place on Tuesday on a weekly basis, and they run through December 15th. They're always starting at 1500 Central European Time, and webinar slides and videos will be made available 1 or 2 days after the webinar on the RAVENNA website. So here's a more detailed look at the program we have prepared for you. Today we are going to talk about AES67 in wide area networks. On December 1st, Luca Giroli from DirectOut will talk about their project, which they call Lockdown Rock, where they had remote musical recording. We have on December 8th, Dirk Sikora from Lavo, who will introduce us to some remote production projects they have just recently set up. And on December 15th, we will have Bill Ronopoulos and further presenters hosted by Ross Video about remote production using the cloud. I already mentioned that there will be one webinar which is not focused on remote session. That's the webinar coming up in 1 week. It's about ST2110-31. That's the bit transparent AES3 transport over IP, also known as RAVENNA AM824 format. Since James is based in San Francisco, we allowed him to start 1 hour later to grab a good cup of strong coffee. So next week, the webinar will start at 1600 Central European Time. And then a week after, Daniel Bulls from Meinberg and I will present on IEEE 1588 2019 and how PTP is or can be used in wide area network application. So that's the program so far. I have 2 words on housekeeping. You should see a question and answer section on the GoToWebinar control. If you have questions anytime during the presentation, please make use of the Q&A. Just send your questions and we'll try to cover as much as possible after the presentation. Okay, so let's jump into the topic. Let's see what remote production actually means and what we are talking about. So we all know the conventional production setup where we have a big event in a venue, the OB van pulls up, a big team jumps out and cameras are being prepared, microphones are being set up. We have the production team inside the OB van with a big desk or 2 big desks and everything. And then we have a readily produced signal, which is fed using SDI, any other appropriate means, back to the broadcast station where there may be some additional keying or whatever processing before it goes on air. So that's the conventional setup. That requires quite a lot of resources and people on location. And we are now seeing that this is going to change into a typical remote production setup. So we just have fewer people on location, just the material, the resources you need to record audio and video signals, send all those signals back as close to real time as possible, and let the home crew at their home base do all the production. And so people don't have to travel. You're saving a lot of cost usually, at least for the travel expenses for the material. Of course, you have increased cost for setting up and operating the wide area network connections. But as we all know, unfortunately, these production scenarios become more and more important as we still are coping with this weird COVID-19 situation. So that's the basic scene. We all know that IP-based signal transport has been in use for quite some time. For example, the SMPTE SD2022-6 mechanism has been used, or any other proprietary means where we have signals being pre-produced on location in the venue, and then instead of just sending SDI, you could use 2022-6 to send the whole pre-produced signal into your back to your home station using IP connections. And of course, the same way you can also use feedback for the operators on location. So that has been in use for quite some time. And now we are trying to get everything in real time over IP or cross IP, across wide area network production back into the remote production studio. Luckily enough, we have a standard for this, which is the ST2110 standards, suite of standards, because it's just not one standard. It's a collection of standards covering video, audio, ancillary data, and even more. That has been originally targeted to being applied to real-time production scenarios on a campus network, on the corporate network, but we are now seeing people applying 2110 also to remote production scenarios, and that's what we are going to talk about in the upcoming webinars, of course. So let's have a quick look at various remote production scenarios. We have the typical remote production scenario where we have a venue, an OB van. They all run their local IP LANs inside. We have a facility which also may have a local IP network, and we need the wide area network in between to transfer the signals back and forth between these various locations. If we open up one step further, we can call this a distributed production scenario. So we add more facilities. We could also add more remote production sites, of course, and just increase the size of the network, the number of participating points that really come into a more distributed production scenario. And the final step, of course, is also going into remote production, is if we add cloud processing. So if we have virtual environment like the Amazon clouds or Microsoft clouds, we can use those clouds to actually set up processing stages and let part of the job, which usually has to be done in facilities, being executed in the cloud. And of course, the question is, we know that in all the local area networks, technologies like RAVENNA and AES67 2110 are perfectly suited to run that. That's what they have been designed for. The question actually is, can we utilize AES67, RAVENNA, ST2110 as well for the wide area network transfer and for the transfer into and back out of the cloud? So what prerequisites exist? What are the obstacles to overcome? What we all know is that RAVENNA and AES67 by definition require high performance connections, which you usually can find in local area network or in campus-wide networks. And the question actually is, what is a high performance network? What is a high performance wide area network connection? And what in contrast is a low performance wide area network? So we can basically classify networks into several categories. This is a very rough categorization, of course. We have local area networks or networks performing like local area networks. We have managed wide area networks, and we have unmanaged wide area networks. So in a local network environment, usually these are the in-house networks. We have the benefits of having high bandwidth available, no packet lost. It's a full switch network. We have usually very, very low latencies and small packet delay variations because of the short distances and little number of hops to cross. We have full quality of service in place. We can even add fully PTP aware equipment, and also if required for mission critical production steps, we can add redundancy in those networks at any point in time. If we open this up to corporate networks, these can be, broadcast stations that have remote locations or even stations all over the world. They usually have their own networks in place, like fiber, dark fiber. They can be permanent or leased lines, but they have full control. That's why we call them managed. Usually they perform very similar to local area networks, although they may have just lower bandwidth available, larger packet delay variation or latencies. They may have limited quality of service capabilities. Mostly they have some PTP aware capabilities as well, and they offer redundancy for robustness and fail-safe operation. Could be forward error correction or other appropriate means. So we can see that we can easily stretch out the real-time production from the local environments into the managed wide area networks. But then we also have the internet. I mean, size-wise, this must have been a different order of size, but the size should just indicate that we have basically no control. The internet, it's uncontrolled, at least not under our control. It has uncertain bandwidth. It has common packet loss. It has large latencies and high packet delay variations. We can't apply quality of service. PTP is not available, and at least no inherent redundancy mechanism is offered by the internet inherently. So in that aspect, the question really is, we know we can simply easily run AES67, RAVENNA, ST2110 in local area networks and mostly also in managed wide area networks. What can actually be done to run RAVENNA, AES67, 2110 across less performance wide area networks? Well, this is just to illustrate this. We definitely can't run RAVENNA and AES67 without further means across the internet. So that is the point where I want to introduce Nicolas to take over, and Nicolas is going to introduce you to the work which is currently going on in AES67 and to the fundamentals which need to be discussed or understood in order to successfully apply AES67 or RAVENNA, ST2110 transport over wide area networks. So Nicolas, you can take it from there.
Yeah. Let's do that. Okay. Hello, everybody. Thank you, Andreas. This is a presentation that I did a lot in the last few weeks, but I extended it especially for the RAVENNA webinars. So you are actually the viewers of an extended version of this presentation. So first, what is a wide area network? So of course, Andreas already gave answers to this question. So you can see that as an interconnection between different sites. For instance, here we have two LANs that are interconnected. You can connect obviously to virtual endpoints that are on data centers or on endpoints that are on their own. And you can use a VPN to connect. You can use the internet, or you can use a lease line. And you may have a gateway, which will allow you to transit that data much more gracefully into the WAN. But then, of course, why would I need AES67 on WAN after all? And that is because of the COVID and because of the rising needs of remote production. So, of course, many of those remote production are file-based. So they don't need real-time audio to be done. But when you're talking about live content or live recording or similar to live production, then AES67 might be a choice, might be a need. And then the question is, how can we put that on the WAN? And this is obviously a question that is shared by many people. So during the summer, we started a project on the standard committee on AES67 development. So this is SC0212M. And that aimed at answering those questions. So what can I do with a vanilla AES67 device on the WAN? What can I add to my network to strengthen the WAN connection? And what should manufacturers add to their equipments? So underlying this, there's the idea of AES67 maybe needing to be updated in order to accommodate the WAN constraints. But also there's the idea of education of the general AES67 community in the specifics of wide area network. And this is exactly the purpose of the presentation today. Of course, the work from the standard committee is still ongoing. This presentation is not aiming at presenting the results from this working group, but mainly giving you hints and presenting some problems that we are trying to solve, or at least trying to present solutions to. So the first question is, okay, internet is IP and AES67 is audio over IP. So they are both IP, and wouldn't then be WAN ready by design? I mean, the WAN network is a network, and you might think that it's as easy as putting in the right IP address to go through the internet. And that's both right and wrong. AES67 was built with LAN constraints in mind. That means that there are small distances, and the network is very controlled, is private, and there's very few restrictions in terms of bandwidth and protocols that are used, which is totally the opposite of a wide area network. You will have long distances, which will mean longer delay. You will use a leased or public network, most likely. So you will have to cope with other people on the network, and therefore to cope with limitations in terms of protocol. Maybe multicast will not be allowed, or PTP will not be allowed, for instance, and limit of bandwidth, because obviously you cannot have as many bandwidth as easily as on a local area network. So typically in audio, what is used is ASIP, the audio contribution over IP, which is described in EBU tech document 3326. And this is very efficient because it allows to adapt to different bandwidths, including the compression of the audio. But of course, oops, it's strange, whatever. But of course, it's not necessarily what you need. So it all depends on the one you own, and there are many different ones. So there's the one you own. If you are a big broadcaster, you might have a one in-house, and then you have a dedicated team for that. So that's not a problem for you. You have the one you borrow, and that is a leased line, and then you have an SLA for that. So you have to refer to the SLA to expect performances from this line. Or you have the internet, and then sadly you are on your own, or almost on your own. And then you have the cloud, and it's more or less the same as a WAN when you're talking about cloud, most likely because you will have to go through a WAN to reach the virtual machine, which will likely be on a data center. But also because while using a virtual machine, you use the supervisor, an hypervisor that will simulate the hardware to run the virtual machine. And this simulation is done via software. So basically, the software time imprecision can be seen as the same as the time imprecision caused by a wide area network. But of course, that's only from the transport point of view. But thankfully, AES67 is only doing transport. So this is what we are talking about right now. So the question is, do I really need RAVENNA and the AES67? Because we saw ASIP. And AES67 differs from ASIP with the following features. So do I need precise timing on my streams? For instance, I need lip sync or even doing a mix minus, and I need streams to be really precisely timestamped. Do I need PCM quality? And do I need low latency for real-time operations? So low latency on a WAN, which may go from 5 up to 250 milliseconds, but low latency still. So if you want all those three, you will need AES67. If you don't need all of those three, they might be easier to use protocols. But of course, it's not because there's something easier to use that this is something you want to use. You may have an already existing RAVENNA system, and your staff is trained on RAVENNA. So what you want to use is RAVENNA all the way, and that's perfectly fine. And from my own experience, using RAVENNA, it's much simpler than using an ASIC codec. So sure, you can use RAVENNA on a WAN, you can use AES67 on a WAN, but you will have drawbacks. So what you gain on one side, in the easiness of using in regard to the training, the current training of your staff, you will have to pay it on the other hand by, for instance, managing your network more properly. And of course, it's all about the use case and the expected performances. This means that you have to define your workflow. You have to know if you need to compensate for latency, if you need precise timing. And absolutely, what is precise timing? Do I need the timing on the order of the microsecond, of the millisecond, or are the timestamps enough? So there are more and more systems that only use the timestamps of the packets, even to do the mixing. So not even PTP synchronization on some processor on the network. And do I need to share everything from site A to B, or do I need the gateway to choose what I share on the WAN? So all those questions will have consequences in your expected performances. And of course, the one that you will be using will have consequences on those performances as well, and might lead you to different answers to those questions. So let's see the different problems that are associated with WAN. First, you have delay in jitter. Of course, this is the most obvious one, because light travel at 200,000 kilometers per second in a fiber. And this is both fast and slow, because it's almost more than 5 milliseconds for 1,000 kilometers. So when you take the example of France, for instance, from Paris to Lyon, it already takes 3 milliseconds to go only on the straight line. And then it's only the straight line. So if you have to account for network topology as well. So for instance, using this network topology, which is the topology of a specific network provider in France, if you want to go from Saint-Etienne to Toulouse, for instance, you have to go all the way through here or through there. So even though it's really short in terms of straight distance, using the network, you will have to go around. And then the time can be much higher than that. And I see it on my home when doing the ping test to the work to the building of merging in Lausanne. So I'm working obviously on a VPN, and and the VPN is the packets are using at least 16 milliseconds to go round trip, so back and forth, and up to, in this specific measure, up to 42 milliseconds. So what this means? This means that sending AES67 packets from Grenoble to Lausanne will at least take 8 milliseconds on this specific network that is from one specific ISP in France. So 8 milliseconds at least, but of course, because you have variations, because it's the internet. So you have different routers, you have different traffic, you have congestion points, you have routes that is evolving in real time, you have media conversion that is multiple gigabits line fed into a 10 gig line, fed into a 100 gig line, etc. So with all of that, you have high variations of packet delay, which here leads to at least 21 milliseconds. So in order to not lose one packet with this specific result here, I need at least 21 milliseconds of delay. And this is where it gets tricky, because AES67 recommendations are not really met in that point, because it's basically AES67 gives a maximum of 20 milliseconds. So here you have already the 21 milliseconds, so half of the round trip, and that's only the bare minimum. So you would want to go even higher than that. So you will see that all in the presentation from director, for instance, later on this on the RAVENNA presentations in December. So then it can be seen as that on the local area network, all those delays, both the geographic delay and the packet delay variation, they are really small. And although the packet delay variation can be high, especially when sending from a software endpoint, for instance, a software driver, it will still be really small in comparison to what you get to the WAN, where the geographic delay will have a very big impact on the travel and on the latency of your system. And of course, this is geographic delay. There's not much thing you can do to lower it. You can, of course, try to get the most straight line in terms of network topology, or you can try to invent the time machine to go faster than light. But all in all, you are limited. So this is the first thing that we tell our customers at Merging, is that do not expect any kind of latency on the WAN that is comparable on a local area network. And this is an example here. So here we are doing a WAN transmission, testing WAN transmission at Merging, and I'm getting back and forth to the WAN and to a server in Frankfurt. and I have to set the buffer to 330 milliseconds, sorry, 330 milliseconds to be able to receive the streams. So this is taking into account the packet delay variation, the back and forth from the server, etc. And when you are okay with all those different timing, the delay and jitter, then you have the timing and seek problem, because AES67 is based on the PTP timescale, which means that it uses the Temps Atomique International, the International Atomic Time, with an epoch on the January 1st, 1970, which means that, of course, if you want to share audio between different sites, the easiest thing and the AES67 way of doing it is to share the same time base. So you not only have to have a master on each site, but the master needs to be in sync. So how do we do that? Well, the simplest way is to use PTP Grandmasters synced with GNSS, Global Navigational Satellite System, so basically GPS or GLONASS. It's expensive because those Grandmasters are generally expensive, although we have Ravenna partners that provide them at a very sensible price, but they most likely are unpractical because you need a GPS signal to do GNSS signal to do the sync and of the master, and those antennas are really how to say, tricky to place. So you may have a site where you do not have the line of sight that is clear enough to have the GNSS antenna. You could do PTP over the WAN, and that is passing the packets, unicast or multicast, over your WAN from one site A to one site B. And this would work as well, but you will get all the problems. You will get a lot of jitter and even asymmetry. That is, your masters, your PTP endpoints, they think they are at the right time, but actually they are on offset. That can be multiple microseconds. So depending on your system, it might cause problems. It might cause problems mainly for some devices that do not cope well with high jitter PTP. Or you can use another means. It's basically you could use other means. Just be creative, because this is a new way of trying to share time on the network. So there are probably many other ways a PTP timescale can be recovered or reconstructed on the software or hardware, and it's really open. So this is an example, for instance, practical example of using a Grandmaster on each site, and those Grandmasters are synced to GPS. So this is how it's done. You have a Grandmaster on each site, and of course, because Ravenna is signaling only the PTP domain, you can do the connection really easily. And for the AES67 in the SDP, you can signal it in a certain way as well with the traceable keyword that allows you in the SDP to signal that, okay, you have to trust me. I have the right reference, and I can tell you that I have the reference from GPS. So if you have a reference from GPS, I guarantee you that we are in the same clock, even though we don't have the same Grandmaster. Yeah, so this is that. And finally, we have stream reliability, which is not a problem. So on the one, you will have packet drops. You will lose packets most likely, because you can have a link failure, you can have a router failure, you can have a network congestion. although you do not really experience them on a WAN, they are very, very often. So you need a sort of redundancy. You need a way to recover the packets that will be lost. And unfortunately, AES67 does not provide any answer on that. But ST2110 does by using ST2022-7, the multipass redundancy, on which we talked a lot during the RAVENNA webinar, if I recall correctly. So basically, the idea of ST2022-7 is I send 2 streams, and using on the one problematic, I send those 2 streams using 2 very different paths, so that I make sure if one path goes down, then the other path is preserved, and if I lose one packet on one side, I can recover the packet from the other side. But there are also other techniques like forward error correction, FEC, or stream reliable transport, or WIST that can be used. So let's see a bit more about them. Basically, FEC is doing partial redundancy. So the goal of FEC is to say, well, if you lose 1 packet, 2 or 3 packets in a row, then I have enough data that I got earlier to reconstruct those packets. But if you lose the stream totally, then you lose the stream, and FEC is not really of any help for you. So depending on the shape of the loss that you expect, you might want to use FEC or ST22-7, or you want to use query requests protocols such as WIST or SRT, which basically, when the receiver is missing a packet, it will ask it back to the sender. And obviously, the problem with SRT is that there is a high latency, much more than before. If you take this example from streaming from Grenoble to Lausanne that I showed you earlier, so 8 milliseconds in one way, 16 milliseconds in both ways, you would want to allow the receiver to ask at least twice the packet, so that if once it's the packet, the packet that is asking missing data is lost, the second time it can recover the missing packet still. So twice that is adding 32 milliseconds at least on the minimum time, 32 milliseconds. So this is going up to 40 milliseconds of link time with an 8 millisecond connection. And if you recall also that the maximum time measured was 20 milliseconds single trip, so it would be actually closer to 100 or 120 milliseconds just to do the SRT from Grenoble to Lausanne. Whereas using FEC, it can be smaller, although you still have latency. And with ST22-7, you basically have only the latency is only the one of the longest path. So this would be in our case, for instance, I would use 2 different ISPs. One is using 8 milliseconds to reach Lausanne. One is taking maybe 20 milliseconds to reach Lausanne. So the latency of my link here would be 20 milliseconds using 2022-7. And of course, you do not really have to take care of that. Some companies are specialized in providing those edge devices that allow you to do tunneling over the WAN, or that will connect to their own server, for instance, of those companies. And truth is, you can even do those gateways yourself if you're geek enough. So basically, the goal of the gateway is to create a tunnel, or to at least shape the traffic from the LAN to the WAN and back to from the WAN to the LAN. So it allows you to do many useful things, for instance, QoS tagging on inbound and outbound. You can do multicast to unicast network address translation. You can do port translation, etc. So actually, using a gateway is really simplifying the life of the system designer. But there are so much more programs that can be experienced on the WAN, and it all depends on the use cases and on the expected performances. So it's really every time it's a different program, and every time the answers might be different. But the good thing is that AES67 is based on IT standards. So with AES67, you are using RTP, and RTP is widely used over the internet, and even at home when you are watching TV with your ISP, the stream might be an RTP stream. AES67 does not require any specific transport equipment, so yes, PTP switches can be used, but they are optional. So AES67 by design can be transported on the WAN, any WAN, and the internet as well. But of course, the problem is that PTP is not designed for WAN. So the problem is with PTP and the timing. And of course, multicast is rare. So be it Ravenna or AES67 or even ST2110, you have to take into account that you might be needing to use unicast, or as seen before, use a gateway to convert your multicast to unicast back and forth. So what should I expect? Well, with care, basically AES67 can go over any IP network. This is a given. The only thing is that, of course, you have to tune your link offset, and your link offset may be much more than 20 milliseconds. And depending on your type of WAN, so if you have a private one, you could be much lower in those link offsets, or if you use the internet, you will be much higher on those link offsets. You will have clock program as well. Clocking programs, so this is up to you on how to set it right. If you don't use redundancy, you will have dropped packets. So this is another thing to fix. And again, the easiest thing is to use a gateway, which would really simplify your life. But of course, we have more and more Ravenna systems that are shipping with ST2022-7. But be aware that using ST2022-7 on a single link, on a single connection, like I have here, is not really a good idea, because you would not really have two different paths, and the fundamental idea of ST22-7 is really the going through two different paths. So system design is key, and it takes time. And it takes time in analyzing the system, the workflow, and the expectancy in terms of performance. Well, that's it for me.
If you're looking for more answers on your questions in general to Ravenna AES67 2110, just go to the Ravenna website. The resources section offers quite a lot of material. Of course, also AIMS and Nicolas mentioned JT&M and others have resources available, which are always worth looking at. And the next webinar, Roland, as you particularly asked for that, is the next week, Tuesday at 1600. As I said, to let James get out of the bed and grab a cup of coffee. He's living in San Francisco. So this is about 2110-31 applications. So for those of you who don't know what 2110-31 is, it's the AES3 bit transparent transport over IP, in contrast to the -30, which is AES67, which can carry only 24-bit PCM data. If you want to transport the full AES3 signal in a bit transparent way, for example, to transport Dolby E and other formats, then you would have to use the -31 standard, or the Ravenna AM824, which is the basis actually for the 2110-31 standard. So to -31, it's been based on the Ravenna AM824 payload format specification. So that is next Tuesday, 1600, and I would love to see you all again on that particular presentation by James Cowdery from Dolby Labs, from Ravenna Dolby Labs. Yes, I guess that's it. that's it for today. It's 1600. We'll make this presentation, slides and video available in 1 or 2 days. And if you have further questions, just drop me an email at ravenna@alcnetworks.de or any other known email address. And if that's for Nicolas, I will definitely forward it to him. And otherwise, we'll try to answer all your questions. And again, please join us for the further upcoming webinars on Tuesdays. So thank you, everyone, for joining in, and have a nice Tuesday evening in Europe, or rest of the day in the US, or maybe rest of the night in Asia. Thanks for joining. Goodbye.